Let's hope that one works. Yeah,
It's slow. Perfect.
All right. Thanks, Kara. Well, to kick us off, we have Darrin York from Rutgers, and he'll be teaching us all about enhancing precision and accuracy in our alchemical free energy simulations. So without further ado, thanks.
Thank you very much. Can everyone hear me okay? All right, cool. First off, of course, I'd like to thank the organizers for giving me the opportunity to talk in front of you all. It's a really exciting conference. Have all specialists in the audience for this sort of thing. And so I'm excited to tell you a little bit about what we have been doing with new methods in Amber. I want to start out with a little perspective. Just to kind of give my sort of perspective, when we do MD simulations, generally when we think about MD simulations, we're thinking about doing a simulation of a single state. What distinguishes free energy simulations from classical MD simulations is we're studying a process where something's actually changing. And so in that sense, we need to necessarily simulate both end states, and in some cases, worry about pathways that connect those two end states, making it a little bit more challenging. So the idea is there's sort of two flavors of this that we typically use, one of which is we look at a transformation along a physical coordinate. Oftentimes in those situations, we're actually interested in that coordinate. It may represent a pathway, for example, in a catalytic reaction, or we may be very, very interested in the path. In another case, we're doing alchemical free energy simulations where we're mainly interested in the end states. And there we can introduce, if we want to, a fictitious coordinate that allows us to make that transition in a way that's easier to compute. And so those are sort of two flavors. Now, formally, these two things are the same, right? You can use the same techniques for both things. You can go along a physical reaction coordinate and constrain your coordinate and do things like calculate a potential of mean force, or you can allow things to fluctuate back and forth, calculate a free energy profile and get pathways in that way. You can do the same things along an alchemical coordinate by fixing a lambda and doing a bunch of windows, or allowing that lambda to fluctuate and do things like lambda dynamics. So it's the same framework, but this is sort of distinguishes those two classes. Both of these classes have many types of things that we need to worry about in terms of challenges. In particular, I'm going to talk today about enhanced importance sampling and the introduction of the need for what I'll call universal model that can know things about electronic responses and bond breaking and forming and changes in protonation states and tautomer forms and things of that nature. So what I'm not going to talk about is the stuff associated with the physical pathways. That's something that we do in studying mechanisms. I'll call attention, because I know this is being recorded, to a bunch of papers that might be interesting. The top paper, if you want, we have a free energy toolkit that allows multi-dimensional variational free energy profile analysis using B-spline basis. It's really, really stable. It's being distributed free as part of Amber tools. By the way, Amber is free now to academics, which is a nice thing to have going on, but this is just sort of an attention slide. I'm now going to talk about Amber drug discovery, and in particular what we're doing with free energy methods in Amber. And before I get started on that, I want to recognize a host of people in my group that have done fantastic work in this area, including Tai-Sung Lee, Tim Giese, Jinsei Zhang, and other folks, and also consulting with a bunch of fantastic academic collaborators, including Bill Jorgensen and Benoit and Zoe, Stefan Borish, Kenny Mertz, and Junmei Wang, and a host of really talented and fantastic collaborators in industry, without which, honestly, we wouldn't have even been aware of many of these problems. And so I want to especially highlight ongoing collaborations with Abir Ganguly and Albert Penn, older collaborations with Woody Sherman, and especially a call out to Charles Lynn, Brian Raddick, and Anna Silvera, with whom we've had many, many discussions, and they've tested a lot of things for us, gave us a lot of really great ideas, and it really took a village to get to where we are, and so I thank everyone before I get started on that. All right, so what I'm going to talk about today is I'm going to sort of talk about slow. I'm going to talk about optimized alchemical transformation pathways and how that segues into some enhanced sampling techniques that we're doing. And finally, I'll get on to some new things that are unpublished that I'm really, really excited about. So let's start out by kind of setting the stage, talking about different tiers of challenges in free energy calculations. So the way I think about it is sort of three ways. Tier number one, if we have compounds that share a common molecular scaffold and it's in a binding mode, we can typically use relative binding free energy methods. if the compounds have different molecular scaffolds, but the same binding mode, we have to do things a little bit more trickily. We don't have the same type of atom mapping. We need to use other procedures, but basically the same idea that a lot of volume is being conserved when you do a transformation. You can still do a type of relative binding free energy and allow minimal relaxation of your environment. But then whenever you have a situation where you have different scaffolds and different binding modes, then you typically have to bite the bullet and look at absolute binding free energy calculations, which have their own set of challenges. All right, so I'm going to talk a little bit of an update of what we've done with soft core potentials in Amber. This is a detail, but it's an important detail. Here's the basic idea. Whenever you're doing calculations in solution, there's a fight going on. Electrostatics are trying to find ways of negative charge and positive charge cozying up to one another, and van der Waals repulsions is providing a Pauli exchange to keep things apart. So the idea of a soft core potential is you want to soften things up. Avoid singularities, yes, but basically everything going on in a molecular simulation, even if you're using machine learning potentials, at least good ones, is that sometimes interactions are hard. And you need to soften them in order to get transformations. So the idea is if you start out with a potential that knows how to balance Coulomb and exchange repulsions, as you turn those kind of off and soften them. So basically what you do is you take an effective distance, and instead of going to 0 where things blow up, you kind of go to a constant. So it ends up being something finite. And so the idea is if you allow your electrostatics to lag behind the softening of your Coulomb, the softening of your exchange, then you won't have things collapsing. What you want to avoid is sort of an overriding of the electrostatics and exchange repulsions causing different types of problems. So to illustrate that, here's what the soft core potentials on the left look like in Amber prior to Amber 18. And what you can see here is I'm showing sort of what the switching function looks like for the Leonard-Jones term and the Coulomb term for a couple of different lambda values. And I've handpicked those lambda values to illustrate something in circles, and that is that you can get a crossover. Crossovers are bad. Crossovers mean you can have this inversion of power where all of a sudden it seems more favorable for me being a negative atom to jump on top of a partially positively charged atom because the exchange repulsion is enough to keep me apart. So CCG sort of noticed that this was a problem. They reparameterized that form, and what they did essentially was made things a lot harder. But then you started to get a gap, and you still could get a little bit of a crossover. Then we started developing new types of soft core potentials which would avoid this. We ended up getting the one to the right, which we think is a pretty good, robust one, and we use that moving forward. Another way of describing this, and one of the things I'll say is these common problems that you see are things like endpoint catastrophes. We know that for a long time. Particle collapse, and something called large gradient jump, which is the sensitivity of the soft core potential to changes in the softening parameters. So another way of saying this is you need to have good phase space overlap, whether you're doing a thermodynamic integration calculation or a bar calculation or M-bar calculation. And so phase space overlap involves the distributions of two end states of the delta E distributions, been described in many papers. But the point is if you go to some different example transformations and take a look at the du d lambda profiles, every time you see these little yellow dots, and I'll highlight just a few of them, what you can kind of see is that if we monitor the phase space overlap, that's what these plots are over here. This is the window before and the window interval after, and here's the window interval where that blip occurs. You always see you go from pretty good phase space overlap to crappy phase space overlap to pretty good phase space overlap. That's where you see those kinks in the du d lambda profile. So we want to get rid of those. And so essentially our new soft core potential does that. But related, so that's what the new soft core potentials do. We've been working on them pretty hard. It's lots of bells and whistles that you can change. But I want to say something more about phase space overlap. So phase space overlap is useful also in looking at things like Replic exchange. So if you're using Replic exchange, it turns out that Replic exchange acceptance ratio tracks really well with phase space overlap. And so what you can do, you can run a quick burn-in calculation, only a couple, maybe 100 picoseconds, in order to get some M-bar statistics, calculate using radial basis function interpolation of phase space overlap, and ask the question, what would be the best lambda schedule to optimize the phase space overlap? Then when you use that lambda schedule, that predicted lambda schedule, so that's what these red lines are, It also evens out the replicate exchange. You get a lot more round trips, and it's round trips that really enhance your sampling when you're using things like Hamiltonian replicate exchange. So the way we do things is we do burn-in calculations that adaptively allow us to choose a lambda spacing for a given number of points that optimizes the phase space overlap. All right, so now that we have good lambda transformation pathways, and we have optimum phase space overlap that allows us to enhance our replicate exchange, now we're going to be talking about an actual enhanced sampling technique. We call this alchemical enhanced sampling, or ACEs. And the idea is that essentially we're using, one thing I kind of want to say. So here's the idea. What we want to do is we want to create an artificial enhanced sampling state in some way. Okay? We want to connect that artificial enhanced sampling state with the real state through replicate exchange, which will maintain equilibrium and get these enhanced sample distributions all the way in the right Boltzmann distribution to our end state. But we're also going to play a trick. In that enhanced sampling state, we're going to have to do things like turn off interactions with surrounding. But we don't want the environment to collapse around it, because that's going to make it really hard to communicate those exchanges back. So what we want to do is we want to have a counterpoised set of corrections, whereas something is disappearing, something is appearing in the same way using a dual topology framework, so that those two topologies basically mean the topologies don't see each other. So something is going to be disappearing as something else is appearing, so there's minimal arrangement of the environment, and yet enhanced sampling through those separated topologies is being enhanced. And this can be a problem even when you have a dummy state. So here's what the potential mean force profile looks for just acetic acid. And what you see in these curves, the top curve is the gas phase free energy profile. The other curve right below it is in solution. And the other two dotted curves, that's two lines on top of each other, that's the potential mean force, both in the gas phase and in solution, of the dummy state. The dummy state where all the interactions with the environment are turned off. All the electrostatics are turned off. It's still, even the torsion angle and 1,4 terms give you a barrier of like 5 kcal per mole. What that means is even in the dummy state, if you approach the system and turn off all your interactions starting in the cis, or starting in the syn, or starting in the anti, you're going to remain trapped in the dummy state, which means you're not going to get the right answer if you do a free energy perturbation where you're trying to close a cycle. So what you need to do is you need to create an enhanced sampling state where all those interactions are really turned off in a way that doesn't sort of expand your volume of phase space too much, but basically turns off all the interactions, turns off all the 1,4s and single bond torsions, but maintains all the improper torsions and things like that, so that you get reasonable chemical sampling, but all the rotatable bonds can be sampled really easily. So the idea is we use that type of a Hamiltonian framework to lower the barrier, and then we use Hamiltonian replicate exchange in order to mix those states along the alchemical chain in this counter-diffusing way so that the environment doesn't have to rearrange very much in order to enhance our sampling. And it works like wonders. It's really good. So here's an example of just looking at some things in solution. So we went to the FreeSolve database. They have some amber results. We picked all the ones that look funky. I don't like that result, doesn't look very good. And we repeated it. So the errors from the FreeSolve database, latest version, for acetic acid and some other things were 4 kcals per mole or so. When we redid these calculations, we got about the same thing. So this is when we don't use any enhanced sampling at all. We just do a normal calculation with Hamiltonian replicate exchange. If we used a REST2 implementation that we did just by reading the paper, so it wasn't FEP's REST2, it was us trying to do the best we could with REST2, it goes down to 2 kcal per mole or so. When we use ACEs, it goes down more to 1 kcal per mole. It turns out that REST2 and ACEs are perfectly compatible. You can use both at the same time. When we actually do use both at the same time, it goes down a little bit more, but it's basically the same as ACEs. So that's just looking at solvation free energies, where you have things that might have different traps in the gas phase and in solution. So this is just guaranteeing that when you get to that dummy state, because remember, you don't disappear something in solution. You don't disappear something in the gas phase. You turn it into a dummy state. And if that dummy state isn't the same, because if that dummy state contains conformational traps, depending on what your starting state was. And if your starting state is different in solution in the gas phase, and you get trapped in the dummy state, guess what? That's not a real salvation free energy because you didn't wind up in the same state. All right, that's a take home there. So aces can be used not only for the ligands, but also for side chains. So if you have a correlated motion of a side chain with a ligand, you can have the side chain be part of the aces region. It's treated with a dual topology. And here's the idea. Okay, so the idea is if you have something like a ring with a substituent that changes, maybe this ring is hydrogen bonding in some way, and you change it into something that won't hydrogen bond. Well, it has two choices. It can move away from what it was hydrogen bonding to, or it can flip. Okay, so if the right answer is flip, well, there's no way it's going to flip if you use something like a maximum common substructure atom mapping, because the only thing that you change is the thing here in the end. And the only way to get from that state to that state is to actually go through a physical transformation of flipping a ring. But with the dual topology, if you select the whole ring up to the single bond, now you have two topologies. Now you can have that other topology without seeing it be in that other state. And what happens is this state just disappears and this one appears. And you don't have to go through that physical transformation that has a huge barrier of trying to flip a ring in a protein environment. So that's sort of an example of how this works. And so this is an example of looking at the rotation bonds. This is just showing that if you do MD, you're going to stay trapped. And if you use aces, after a certain amount of calibration, you end up getting the same ratios of the different populations because you're getting this enhanced sampling. But it's focused enhanced sampling, right? Enhanced sampling with free energy, be careful what you ask for, right? So it's something where you want to focus the enhanced sampling on the thing that's really going to affect your free energy without enhanced sampling that's going to cause other stuff to fall apart that you don't want to fall apart. All right, 10 minutes. Okay, cool. So here's something really cool. Talking about precision. Here's another thing that can happen with your free energy calculations. We said you can start from one state to another and not wind up in the state that you expected. You want to be able to connect things. This happens all the time in absolute binding free energy calculations. Take a ligand, you make it disappear. Take another ligand, you make it disappear. Well, if you look at the ensembles of your apo state, are they the same? If they're not the same, then that affects your free energy. You didn't wind up at the same endpoint. Same thing happens every time you do an edge. Transformation between ligand 1 and ligand 2. Okay, we're doing some enhanced sampling just by doing that alchemical transformation. And if I'm a different edge that connects to the same node, well, can I go back to that node and say, does this ensemble and this ensemble, they look exactly the same? That's the first thing I ask my students. They say, well, no. And I said, well, then our cycles aren't going to close, where it's like watching the end of a fire hose go all over the place. We got to somehow anchor that point. So how do we anchor that point? Well, we do a simulation of just that end state, and we use a new type of end state alchemical reservoir. So we're going to pre-compute that end state, going to store it somewhere, and now we're going to do reservoir replica exchange when we're doing the real calculation, such that every 20 steps, I'm going to go to that end state, toss it, and grab one from the reservoir so that it's constantly filtering in back into this exchange chain and mixing in through replica exchange, and all endpoints will do that. Now, there's some tricks that I'm not going over. I don't have time to go over, but I'll happy to answer. The trick is, how do you do the mapping of the dummy atoms? Because when you're actually doing an alchemical transformation, he's not an end state. He's my end state. He's not an end state. He's actually ligand 1, but he's got all the danglies to whatever I am on top of him, and that actually is going to affect the energy. If they're connected in the right way, they won't affect the net potential mean force on him, and that'll be okay. That's called a Beresh restraint. But there's ways you can map these dangly things onto the end states in a rigorous statistical mechanical way so that this works. So here's an example. This is just showing, I don't have too much time, so distributions are sort of preserved. So this is using reservoirs. So this is what some different profiles look like in the real state, using one of tandem AI's force field. This is the dummy state. Notice that this just means we're in a conformational trap. Here's what happens with reservoirs. You get the right distribution, but here's the dummy state. You still have traps. Here's what it looks like with aces. Again, you get the right state and you get sort of uniform sampling along that. But here's what the results sort of look like. This is just taking a look at cycle closure errors in solution. Okay, so this is using Hamiltonian replica exchange. These are all errors all those numbers that are minus 2.29, 0.94, those are all supposed to be 0. They're all cycle closures. Okay? When we turn on aces, they get a lot better, but they don't completely eliminate the problem. If we use reservoirs, this end-state reservoir Hamiltonian without aces, but using Hamiltonian reciprocal exchange, they're about as good as aces. When we do both aces and reservoir, it nails it. Nails the cycle closures. So this is going to be really critical, especially with absolute binding free energy calculations. Here's what happens when we look at a system with some different scaffolds. This I just got like 2 days ago. These are a couple of edges. Here's the one cycle from these different things. This is a BRD4. When we use aces, which is like our good method, we still get a cycle closure error of 0.9, even though statistically, our bootstrapping error bars say we're at 0.3 kcal per mole. And this was like with 5 independent trials. Okay, so the idea is you can't rely on error estimates because they only know about the free energy basins that you actually sampled, not the ones you completely missed. But theoretical constraints like cycle closures do. That's why I think they're valuable. When we go to aces with reservoirs, this goes away. So I think this is going to be a really transformative thing for people to do. And now, if you screw up your end state and put it in a reservoir, that doesn't mean your answer is right, but at least it's going to be consistently wrong. All right. So now I'm going to talk a little bit in 1 minute. I'm just going to tell you, so this is going to be an advertisement plug. So we've been developing machine learning models in order to do end states. The idea is we use what's called a QM/delta MLP. So we're basically using machine learning correction on top of a fast semi-empirical quantum model that knows about electrostatics. So we don't have to teach it physics that it already knows. We already know how to compute. We use a so-called bookending strategy in order to graph these end states. So we do transformations of the alchemical steps and then endpoint corrections in order to correct the final energies to this high-level stuff. And we can do that at low cost. So we have to do the highly precise stuff at the level and then the more expensive stuff at the QM level just at the endpoints. So we have a couple papers on this quantum interaction model that we have that's called QtPy. It uses 3-layer neural network using DeepMBKit. We have several papers on it. I might want to encourage you to do it. Some of them are using path integrals and other kind of fancy stuff. But here's the take-home message. Here's QtPy. Here's like robust forces. Notice it also has Ani1x, Ani2x. And the thing you might want to remember about Ani1x, Ani2x, it doesn't know about charge. That's not an input to that model. So it can't distinguish between nitrogen trioxide and a nitrate ion. So it can't do things like look at changes in charge state. So anyway, if we look at non-bonded interactions, we have accuracy, pretty good accuracy for tautomers. And then protonation states, we have really good accuracy. That's where you see things like the Ani models like do really horrible because they don't know about charge. So looking at changes in charge state is kind of waste time. So anyway, I'll finish up now. We also looked at hydrogen bonds and tautomers for nucleic acids because I'm interested in nucleic acids and things of that nature. But it's a cool model, and we're continuing to develop it and are excited to see where that takes us and would like to collaborate with folks that are also interested in similar things or have similar models. We're also developing infrastructure within Amber to do other models just to be able to compare. And with that, I'll discuss takeaways, but I want to get to my acknowledgement slide just because it's important to really call out the people who have done that work, and I want to have time for at least one or two questions. So thank you all for your attention.
Thanks, Darrin.
So is the ACE, do you have to pick the ACE region or is it?
Yes, you do. You have to pick the ACEs region, and here's the best way to pick the ACEs region. You focus on that graduate student who gave you the result that you didn't like. And then you say, what did you choose the ACEs region for? And then you say, I don't like the way that this is where you need someone like Bill Jorgens and say, oh, you need to have this conformational discrete. It looks like there should be a hydrogen bond here. I don't have a good automatic way of doing it. Usually, though, what we do is we tend to take whatever group we're changing and choose the ACEs region so that that group, whatever the first rotatable bond next to it is, will include all that. Like typically it's rings that are flipping that are our biggest problem, but I don't have a good automatic way of doing it. I don't know if that was your question, but yes, you have to choose the ACEs region.
I was doing photon feature, which keeps the structural planar. If you ace it, that would be bad.
So actually, that's the first thing we screwed up. was our first version of ACEs. We turned off all torsions. And then all the things that should have been flat got all wonky, and we had to put that back in and say, okay, we don't need that, but we need to turn off all single bonds so that we didn't have that same problem. So that was our first goof, but now that's been fixed, and there's an option in, amber. There's always options in amber. You remember, with you're using amber, use the make sure random crash is turned off, things like that. Important things.
Well, thanks so much, Darrin.
All right.
Let's give him a round of applause.
Thanks.
All right. So our next speaker will be David Perlman. Get everything set up.
It should be.
So David's coming to us from Q Simulate here locally, looks like, and teaching us all about incorporating quantum representations into our free energy methods.
All right, so it's,
Hopefully we get it set up.
are we, is it not like that? We tried, earlier we tried it, it worked fine.
Yeah, it should work okay.
Okay, it
Yes.
sees it, all right.
There we go. Thank you.